All right, so you can see in the diagram I've drawn the complex numbers, we'll call them W, this omega, but we'll say W1 and W2. They have a modulus, so they both have length 1, and their arguments are alpha 1 and alpha 2. So if I were, it's going to be difficult, but that would be alpha 1 up to there, and alpha 2 is all the way up to there. That's alpha 2. Okay, you can see I've drawn a parallelogram, and of course it would be a rhombus because all lengths are equal to 1 because of the modulus of 1. Okay, so we've got this nice rhombus. So actually remembering that a rhombus has some nice properties, like the diagonals bisect. So this is 90 degrees. This will be 90 degrees here. That will be very helpful. All right, the line I've drawn in from O to P, of course, is if I add those two together. So I'm adding W1 and W2 together to make that line there. Now, if we know that the OP it's a perpendicular bisector of the vector from between W1 and W2, I can just say something like, well, we know that the argument of W1 plus W2, if I'm looking at that argument, so if I'm adding them, so I'm looking for, I'll do it in blue, the argument of that one, which is that one. Okay, so think about this. If I take the whole of alpha 2, which is, no, I need to colour code. I'll do it in yellow here. So the whole of alpha 2 and take away alpha 1. Think about alpha 2, take away alpha 1. That's just this bit here. But we know that it's perpendicularly bisected. So it's cut in half. So it's made up of two parts. So if I divide it in two, each of those bits there is the same. It's alpha 2 minus alpha 1 on 2. So if I take one of those parts, just one, and add it to alpha 1, I've now got the argument of OP. Okay, so I've just taken it in little segments. Put that together then. Put that together and you can see we have half of alpha 2 minus alpha 1 plus 2 alpha 1s, which is the same as half alpha 2 plus alpha 1. So that's the same as alpha 1 plus alpha 2. So just doing a little bit of logic, having a look at those by observation, having a look at those angles, you can see, or you can figure them out. All right, why is that important? So we want to show that actually argument of W1 minus W2, so really that argument is equal to half A1 plus A2 minus pi. Okay, so it's got a minus pi in it, so it's already giving me a bit of a hint, because at the moment I've got half of A1 plus A2. So what I can think is, how is OP related to what I'm trying to get? And I can see that, well, I can kind of tell I'm going to have to rotate it by 90 degrees. So what can I rotate by 90 degrees? What would I get? So if we look at W1 minus W2, so the vector from W2 to W1, like that. Okay, that vector is represented by W1 minus W2. Okay, so if we have a look at that vector and you rotate OP, which direction would be rotating OP clockwise, because that's 90 degrees there. We'd have to rotate it clockwise to get that vector W2, W1, that vector there. So we can rotate that vector, that OP, so OP, which we know, so if we're looking at the angle already, it's half of alpha 1 plus alpha 2. And to go anti-clockwise, we know that we're adding pi, so pi on 2, 90 degrees. So if we're going clockwise, we're going to subtract pi on 2. So we're taking this and rotating it 90 degrees to get this vector here. Okay, and that gives us what we want, because if we have a look at it, they all factorise by 2, 1 on 2 I should say, and we get that. So this argument here, argument of W2 minus W1, is equal to half of alpha 1 plus alpha 2 minus pi.